we will discuss what is known as a linear regression and the simplest method for solving that problem. So just to recapitulate once, we loosely define system identification as a, that is, if you are given a set of process signal values, we are talking about process signals because we are generally concerned with identification of, calculation of models for dynamic systems. So they will have, based on their input and output signals. So given a set of process signal values over time, some model structure we have to assume, and some, obviously some error criterion we have to assume, and also we could have, about the system we will have certain a priori knowledges. We have some experience with the system, so we know some things already. Even if we do not know the detailed model set, we know certain things. So we should obviously try to use whatever knowledge we have while trying to look for models. So then we may have a set of axiomatic constraints for the model to satisfy, that the system is stable, or that its DC gain is positive. Some such facts we may have. So given these things, we have to determine a model that results in the least approximation error according to this criterion. That is the problem. Okay. So before talking about, we are concerned with dynamic models, systems, typically linear dynamic models. You can say systems which are describable by transfer functions, loosely speaking. Okay. So, but before that, actually this problem is much more general, and that's why we want to look at it as a linear regression. Remember that one of the first system identification exercises which we have done, probably all of us have done in our school, is when we tried to do some experiment in the physics lab or in the chemistry lab, and we got some points and we tried to fit a line through those points. That was our first system identification exercise, to be precise, because you are given a set of data points which you got from experiments, and you know a model structure which is given by some physical law, maybe Ohm's law, and you want to fit a best fit line. Best fit in what sense? Best fit in the least square sense. So you have a model structure, you have a best fit criterion, and you have data. And sometimes you may also like to incorporate a priori knowledge, in the sense that you may like to ensure that the line passes through the origin, let us say. So some such things you may also like to incorporate. So that was one of the first system identification exercises in a general sense, which all of us have done. So in that, we actually that is not a case where we are having a timed sequence of signals from process models, but the method is absolutely similar. So first of all, today we would like to see how to do this model fitting, not necessarily for a sequence of signals yk and uk, but for arbitrary measurements. We have some observations and we have a response, and we would like to fit a model. Those responses could be so many things. The index may not be always a time index, right? So later on we will specialize this method for our case, where we want to identify a transfer function. We'll show that many of these transfer function identification problems actually finally boil down to a linear regression, right? So first let us try to see some results on linear regression, which is much more general, which can be used to relate so many things. Economic phenomena and whatever, physical experiments, using a linear model, right? So in linear regression, we typically use a model like this, where we have some responses we have, right? And we want to know, for example, and we have some responses, and we have some what are known as, sometimes known as explanatory variables. So we want to know how this response depends on these explanatory variables. In this case I have written them using a vector notation, but actually it will be like, you know, phi 1 theta 1 plus phi 2 theta 2 plus phi 3 theta 3. So these phi 1, phi 1, phi 2, phi 3 are generally called explanatory variables, things which explain how this y has come, and this theta 1 up to theta n are the parameters. So we would like to find out suitable values of theta such that these variables can explain this y. That is the problem. These variables could be anything. Okay, and obviously we will not be able to, given a set of data, there is no guarantee, especially because we have assumed a linear structure. There is no guarantee that we will be able to fit it exactly, right? Never when we fitted a best fit line, always our points were on both sides of it. So there is going to be some error. So that error, I am simply saying that if I fit using a parameter theta, correspondingly I get an error. Now remember, here I would like to mention one very fundamental fact which you should remember whenever you are dealing with an identification problem, that this model is simply a postulate. That is, we are looking for an explanation between variables phi 1, phi 2, phi n and y using this model structure for whatever reason. These models may have been generated, how this data has been generated, that's a totally separate thing. For example, this data might have been generated, actually when it was finally came, it might have come due to many other reasons. Some of the explanatory variables may not even be included here. That's possible. Or their laws may not be so simple linear case. So we are not, when we are trying to estimate using this model, so there are two things. One thing is the data generation mechanism. For example, suppose I have input and output data generated from a fourth order system, suppose. So I have simulated the data using a fourth order model. Now I can say that no, I want to fit a first order model to it. Let us see what happens. So it's not necessary that if I am estimating a first order model, data has come from first order model. Data might have come from some nonlinear process. So distinctly there is a data generation mechanism, that is the underlying system which has given rise to this data. That is one entity, and the model that we want to estimate is another entity, and these two are distinctly different entities. They need not necessarily be the same. So here we are not saying anything about how the data is generated. We are simply saying that we have some y's, we have some phi's, and we would like to fit a model to it. However, I mean, as accurately as possible. Whatever we will not be able to model will be captured in V. That's all that we are saying, right? So, and in fact there may be several. Second thing that I want to mention is that it is not necessary that these functions, when I say a linear regression, I mean that it is linear in parameters. Here you may have, for example, a very typical case will be that y is equal to, say, a1 plus a2 x square plus a3 x cube. This is a model which is non-linear in x, but it is linear in the parameters a1, a2, a3. So what we mean is that we mean linear in parameters. That's why it's called linear. So it's not linear, it may not be linear in the signal elements. When we say linear systems, it is linear in the signal elements. In this case we are talking about linear in parameters. Okay, signal elements may very well be non-linear, doesn't matter. So this must be remembered. Now sometimes, especially if we want to get analytical results, we will have to make assumptions about how the data was generated. Without that, if the data generation mechanism is left unspecified, you cannot get any results about the quality of estimates especially. So you will have to make very often you will have to make assumptions about what model generated the data. So for that, at least one thing is clear, that if your method is good, then if the data is generated from a first order model, and if you are trying to estimate a first order model, then you should get a good estimate. At least that much your method should be able to do. So to be able to verify that, very often we will make assumptions that about this system data generating model, and very often we assume that the data generating model is also this of this form. Only thing is that in that case we will assume that there exists some parameter theta naught which has given rise to this data, and when you see what, let me explain this, because this will come again and again, that there is some phi's are going in, okay, so y is coming out, this is your system. So how y is coming out? So there is a system parameter theta naught, and there are some disturbances E. These disturbances are are properties of a system. Now this phi and this y you are feeding to your estimator, and so now this is your estimator, this is your system. So system used some theta naught and some E to generate this y from this phi. These are unknown to us. Our objective is to find some value theta using our estimator. So we will feed y and phi, and for this value of theta we will get some value of v. So this theta naught and this theta are going to be distinct. This E and this v are distinct, ideally speaking. And now at least we'll once we do that, then we'll naturally like to see whether theta will be close to theta naught. So such properties we'll look for. So very often we will assume such model structures for the system also, but we must remember that exactly the disturbance values that the system used for generating the data and the disturbance that you got from your model mismatch are different things, right? So these things should be clear right in the beginning, because sometimes they get mixed up because they are same forms of models. So you don't know which one are you using. Are you using the true system model, which is unknown, or you are using the estimated model? You must be able to distinguish between them. When V may represent effects of measurement errors in y or phi, and it will affect I mean various kinds of things like the unmodeled dynamics or your estimation inaccuracy. So many things will come. So having said this, let us try to find out first of all what we would ideally like to do. This V is simply an error in fitting, that is something which we could not fit. But ideally the best would have been if I could have found out a theta which would exactly satisfy y is equal to phi transpose theta. That would give me zero error fitting. Now the question is, can I not do that? I can certainly do that in this equation. But in general the point is that I am not going to fit it for one point. I have say 10, 12, 15, 20 points, and I have to fit all of them. Right? That is the problem. So actually I have a set of such equations. So actually my set of equations are y1 is equal to some phi 1 transpose theta plus v1, y2 is equal to phi 2 transpose theta plus v2. In this way I have say n number of data points plus vn, and I want to find a single parameter vector theta such that all these equations are satisfied in the best possible manner. That is my problem, because I have a number of experiments. When you did in your physics lab, you had a number of points, and you want to fit one line which will approximately describe all these points, right? So now when can you do that? Firstly, can you solve it exactly? It's a very simple thing. I mean, it's a linear simultaneous equation solving problem, that you have to solve a set of linear equations for those unknowns. So when can you solve it? So if your number of unknowns is n, that is the dimension of theta. So if you have number of equations less than the number of unknowns, then you have infinite number of solutions, right? If you have number of equations is equal to number of unknowns, then you have an exact solution. When provided that the given set of equations are independent. If they are dependent, you don't get it. Secondly, that this, so obviously now why you could not do this? Suppose you have n equations, rather suppose you have capital M number of equations, and you have, and this dimension is n. So you take the first n equation, invert, solve the equations, so you will get one value of theta. Now the point is that if you took any other different set of equations, suppose you took these n, you can again solve. You will get a different theta than what you got in the first time. So if you try to solve exactly, then there will be no single theta which will satisfy all the equations, because your number of equations are more than the number of unknowns. So when this is the most typical situation, when the number of equations is more than the number of unknowns. So in that case, what you would like to do is that you would like to get a good approximate solution for all the points, rather than getting an exact solution. For example, typically speaking, if you have points like this, you could take these 2 points and then find out one line which will be quite erroneous with respect to these points, or you could take these 2 points and then find another line. So in general you will find that if you do that, you will get very large errors with respect to the other points which you have not included in your fitting. So what you must do is that you must find a line which does not satisfy any of these equations exactly, but satisfies all of them approximately, right? So you must find an approximate solution for the whole data set. So that's what we are going to do. So method is usual and simple. That is, first of all I define a sum of errors. So if I chose a parameter theta, then what would have been my error in estimating for each one of those points, and then I make a sum of squares, and I say that this is my performance criteria. So I want to minimize it, so find theta which minimizes this. That is the problem. Now this can very easily, you can understand that this can be written like this, where this y is nothing but, so I have written it in vector matrix notation. So basically all these equations if you stack, so y will be equal to y1 to yn, this is your y, capital Y, is equal to your matrix, this is your phi 11 to phi 1 n small n, and this is phi n1 to phi n n. This is your capital phi matrix, this is your capital Y matrix, and theta is theta. So all these set of equations you can write like this, y is equal to phi theta, that is your matrix equation. So if you want to find out this square, it will be y minus phi theta transpose y minus phi theta. That will give you Vn theta. See, this y is a column vector. So if you make it transpose, it will become a row vector. This will become a column vector. Multiplication will give you a scalar, which is this sum. You can verify it very easily. So our usual way that we have to differentiate it with respect to theta and then set it to 0. That will immediately give you, if you try it, it's very well known, nothing great about it. We have also done it in other contexts before. So it will immediately give you that this is the least square solution to this problem, provided the inverse exists, provided this inverse exists. Otherwise you cannot obtain it, obviously. So this is your least square solution to this problem if this inverse exists, otherwise there is no solution. So now what we'll do,
sir, this phi is the measurement of the assumed model.
Phi are the explanatory variables. You have some variables you have measured, and you want to using these variables you want to explain another variable.
This is of the model.
Of the model. Yes. Now, when signals are common to models and systems, signals are generated from system, but we don't know how they are generated. But we would like to postulate some form of the model, and then we would like to find out the best parameters within that form, which explains these signals the best.
So what exactly theta?
Theta are a set of parameters. And they could be resistance, inductance values if you have a circuit.
Model parameters?
Yes, model parameters. Right. So this is my least square solution. Now, obviously, these concepts are by now known that in various situations we would like to, I mean, every time I get a new data, if I have to solve this matrix again, remember that this matrix, this side grows with n. N is the number of data points. It's actually a very large matrix. So I mean, every time you get a new data point, if you have to again recompute this from fresh and then solve it, it's a big wastage of computation. So we would like to recursify it. That's very simple. So it turns out that now you see that I have just written if you have one more data point, then how does capital Y look in terms of small y. So another element, so it is like this previous yk and then another element added at the end. The vector will become one more element longer. Similarly, this phi matrix will become the old matrix plus another row at the bottom. Correct? Theta is same. So if you define that pk is now we have to find out, basically we have to find out that if we know the solution, if you have already computed this solution for k sets of data, how I can use that solution and then make little update so that I get the same solution for k plus 1 data without really recomputing this equation. That's what I am trying to do. So I am defining this is just simple, I mean, mathematical manipulations. So I can show that theta hat k plus 1 will turn out to be, I have defined this inverse as pk, this whole inverse. The whole solution is, the actual solution that I want to compute is this inverse this. So this inverse for k elements I have defined as pk. So obviously, what is my theta k plus 1? It is pk plus 1, phi transpose k plus 1, yk plus 1. This is pk. This is p. So p phi transpose y. So now I am just simply writing it in terms of the previous ones and the new data points that I have got. I have to express that. So that's just manipulation. So if I manipulate, this is the simplest possible derivation I got. There are more complex derivations than this, but it turns out that this is your update. So if you already had computed the least square solution for k data points, then a new solution that includes k plus 1 data points will be given like this. Again, you see the same form everywhere. You will get the old solution plus another correction term. That correction term will have a gain and it will have an error. Everywhere this thing comes. All estimators will have this structure. So here is the old estimate plus a correction term. Same thing used to happen in the Kalman filter. X hat k given k is equal to x hat k given k minus 1 plus kk into same thing. So here also you are having a gain vector and you are having an error. This is the error. So the question is that the old parameter, can it explain the new measurement? If it can explain the new measurement, then this error will be 0. If it cannot explain, then it needs to be changed. So now this decides, so this says how much, what is the magnitude of change, because this is a scalar, and this decides that the change should be made in what direction, right, because this is a vector. So everywhere you get the same thing. You get the same thing in observers, you get the same thing in Kalman filters, you get the same thing in parameter estimators, you get the same thing in neural network training. Everywhere it is the same thing. So this is your update equation. Only thing is that you have to compute this now. So you have to update this also. So for updating this, we use what is known as the matrix inversion lemma, which says A plus BC. This is an identity which holds for, I mean, dimensionally compatible matrices. You have to remember it. I mean, not the form, but you have to just remember that such a thing exists. Don't think that you have to remember it and then recite it anywhere. Usually it is available. So so then using this lemma, pk plus 1 will be given like this, which again has similar forms to that of the Kalman filter. Incidentally, here I have written this I, but actually this thing turns out to be a scalar. This is a number. So you could also write p phi transpose p divided by. When you have a scalar, you can generally write divided by. When you have a matrix, you write something inverse. So this turns out to be a scalar. Why? Because, I mean, if you just check dimensionally, this would turn out to be a scalar. So this is my recursive least square estimator, right? So what have I done? I have first got a set of measurements. I proposed a model form. I simply fitted it in the least square manner, and then I found a way of updating my least square solution if I get another measurement. That is, so I can do it recursively. Every time I get a new measurement, I can just once update this equation, that will give you the new least square solution. So having done that, we need to know how good this estimator is, right? And we need to answer one very important question. Definitely this will give me the least square error, whatever way the data was generated, because that is the explicit thing. For those data points, you cannot get a linear estimator which will give you lower square error. That fact is true. Whether the data was generated by a nonlinear system or not, that is true. But why are you making this estimator? You are making this estimator because once you find those thetas, you are going to use it on other data points. See, normally, why do we build a system model? We build a system model because we are going to use that model elsewhere. So typically speaking, this we must remember, this is another thing, that we typically use some amount of data for building a model, and we employ methods such that the model that we get explains that data very well. That is basically by virtue of our method, or for example, in this case, we got some data points y1, y2, y3, yn, and we found a least square estimate. So particularly for those set of measurements, the parameter vector that I have got naturally will fit those data. It is forced to fit that data. But the question is that now, can I use this parameter theta generally? That is, can I take this system and then in future generate different data and then use this parameter to explain it? Will it work? That is the main question. In other words, can the model generalize? It has been built using a certain data set. Does it work well for other data sets? If it doesn't work well for other data sets, that model is useless. So we always look for a kind of generalization property of models, right? This is a big thing which has to be ensured with neural networks. Otherwise, I mean, a neural network could, it could also happen for a neural network incidentally, which generally does not happen here, is that it could, the given data set, it could model so nicely that it will work badly for other data sets. That also could happen. That is, you could have overfitting, not only underfitting. So for that matter, so therefore, with respect to this data set, I will get least square error, no problem. But the question, but if I want to now suppose, so now what is the question I am asking? When will this model work well for other data sets as well? When will it work well? So if you want to understand that, then you have to make an assumption about the system, how the data was generated, that is how the system generates data. So if you assume that the system generates data using a same kind of data set, this is the way the system generates phi. Given phi, the system gives out y. This theta naught is unknown. It is inside the system. Now you have got one set of y's and one set of phi's, and you used it in your estimator and you got a theta. Now if you take another phi from the system and another phi from the system, will this theta work for this? That is, say this is the first data set, if this is the second data set, then will y2 be also given by phi 2 theta plus some error v, where this error will be small? Will it work? Obviously it will work if this theta is close to this theta naught, because the system generates data like this. So if this theta is equal to this theta naught, then for all data sets it will match. So therefore it is relevant to ask, that is, whether this theta is close to this theta naught if we assume that the system generates data using the same form. That is why it is relevant to ask for this problem, to ensure that your model will be of general usability. Okay. So therefore we will look for such properties. For example, so first of all I will assume that the data is generated by this model, that is, this is the system model. So, and I have taken n such data points which have come from this system, and I have estimated a parameter vector. So now I am explicitly putting hat, meaning that it is an estimate of my model. This is the true model. True means something which the system itself is using for generating data. So obviously we would like to know, I mean, it is therefore important to ask whether this is close to this or even equal to this. Does it happen? So it turns out that if you do a little bit of manipulation, and if you use this relation between y and phi, which is the property of the system, that theta hat n turns out to be equal to this theta naught plus this term. So this will be close to the true one which the system itself is using, provided this term is small. Now when is this term small? Either when this term is small, the second term b is small, or when this bracketed term becomes larger and larger, because this is inverse. So it is like, you know, y by z. So when does y by z become small? Either when y goes smaller and smaller, or when z grows larger and larger. So it is important to know whether that happens in our algorithm. Only under that condition, even with the same system and model structure, you can hope to get the true parameter which the system is using. Otherwise, even using the same model structure, you cannot. Your estimator will never give you the true model. So it does happen under certain conditions. So what are the conditions? First condition is that this goes to 0. How do we say that this goes to 0? When will it go to 0? When this vk and phi k are going to be orthogonal or uncorrelated over sum, because this is like an expectation, right? So that is why these are reasons for which you will find such assumptions are made, that the noise which the system is which is going into the system is orthogonal to these data points. And we will see that in our dynamic system estimation, sometimes that happens, sometimes that does not happen. So for some model forms, if you write the model structure, transfer functions in a certain way, that may happen. If you write it in some other way, it may not happen. If it does not happen, then you have every chance that you will never get the true system parameters. It is possible, even though your data will be fitted in the least square fashion. Data will always be fitted in the least square fashion. About that there is no doubt. So the two typical cases which will give good results are, firstly, that this is we often assume it to be zero mean white, because this zero mean white will ensure. Actually what we need is that vk is uncorrelated with phi k. This is all that we need. But in many cases, if you assume v to be zero mean white, this is satisfied. We will see that in the case of our transfer functions. Right now we only say that vk is uncorrelated with, have to be uncorrelated with phi k, and this Pn inverse must remain non-singular and must grow in size. If it grows in size, then this term will be smaller and smaller, and my estimate will come closer and closer to this true system estimate, right. So this, now there are several nice properties. These kind of results are called asymptotic, in the sense that we can only show that eventually as n tends to infinity this is going to happen. Now this n tends to infinity thing is, it is a result which, it is something, it says that okay, if you do it long enough it will happen, but this long enough is how long? Because in general you are going to only work with finite data. So you are very interested to know that does it happen within 100 points, within 200 points. Finally it goes to, something goes to 0. Now something can go to 0 like this, something can also go to 0 like this. So is it that this is monotonic, it will always reduce, this is not monotonic, sometimes it may increase, sometimes it may decrease. All we are saying is that it will finally go to 0. So typically if it does like this, it is likely to take longer. So we are also interested to know that what more we can say about the estimates. Can we at least say that this performance criterion is going to come down monotonically? Then at least I have little better hope that it will probably converge a little faster than if it were non-monotonic. So now we can prove several such cases. For example, you can prove that if you define a performance index like this, now why did you define it like this? What is the relationship of this with the original one which you are minimizing? The reason is that you have put this pk inverse. Now there is a reason why you have put this pk inverse that will soon come to, but suppose if you define a performance index like this, which is theta k minus theta is the true one, which is theta naught, and this is your estimate. So you are taking a weighted sum of the error in your estimate, right, and you have chosen the weight to be pk, so the weight is also changing. Why did you choose such a function? For one reason, that this weight incidentally goes on increasing with k. So you are gradually having larger and larger weights, this element. Now if you can show that, just imagine that suppose you have a quantity y is equal to lambda x square. Now this lambda goes continuously increases, and then you can show that this y cannot increase, it is bounded, it will not increase ever. So if this is increasing, this must decrease, is it not? If this is bounded and if this is continuously increasing, then this must be decreasing, right? So this our x is like this. So we are going to have this argument that if we can show that over k this q does not increase, but this keeps on increasing, then I will be able to infer that this keeps on decreasing, right? So it can be proved that with this thing, the performance index, that is q at theta hat k and q at theta hat k minus 1. If I take this performance index, if I evaluate at k minus 1 and at k, it turns out to be like this. So at least if in the system there was no noise, suppose this vk is 0, that is the system generated pure data using some unknown parameter theta, but there was no noise, then this is a purely positive quantity. See, phi transpose p phi is a positive quantity, phi transpose p phi is a positive quantity, so their ratio is also a positive quantity. This epsilon square is also positive, here is a minus, which means that q theta hat k is strictly less than q theta hat k minus 1. It will be less than or equal to, it cannot increase. So this performance criterion can strictly, if the system did not have a noise, then this performance criterion would have can only decrease while this goes on increasing. What will it prove? It will prove that this must always decrease. So the parameter error will strictly come down. It cannot increase. So the convergence is not like this. Convergence is like this, right? And why is it an increasing sequence? That is, why is this a more positive definite matrix than pk minus 1 inverse? Because pk inverse is pk minus 1 inverse plus phi transpose. So if you take any vector z and do z transpose pk inverse z, then it will be z transpose pk minus 1 inverse z plus z transpose phi transpose z. Now this can only be greater than or equal to 0, because it is a product of, if you call z transpose phi equal to w, then it is like w transpose w. So if it is w transpose w, it cannot be less than 0. It must be greater than or equal to 0. If this is greater than or equal to 0, then which means that this is a more positive definite matrix than this. Correct? So in that sense, pk inverse keeps on increasing. So therefore you can do it much more rigorously mathematically, but you can show that it will continuously decrease. So at least you know that if your model structure was correct, that is, if the system indeed used some unknown theta and generated the data using y is equal to phi transpose theta, then your least square algorithm will eventually find that theta, if it is presented with enough data, right? So you can prove many other results. For example, you can prove that, in fact we will do some of them in our tutorials, that as k tends to infinity, what does this mean? This equation means what? If we can prove it, it means that the parameters will finally converge to a constant value, because if k grows large enough, then k plus 3 and k will be same, k plus 5 and k will be same. For any finite L, these parameters are going to be same, which means that the parameters will not continuously change. They will finally come to a stable value. So you can prove many such results. This says something about how fast it will converge. So this is a sum. The sum itself will be less than infinity. If you want to understand these things, you have to understand properties of infinite series. So that we don't intend to do, but all I wanted to say is that you can show that if the model structure was ideal and if there was no disturbance, then the least square algorithm will converge to the true parameters monotonically. So at least it has some good properties. Now the question is that this is one way, but sometimes you can ask that, okay, you can ask many other things. For example, you can ask that if I consider the general class of linear estimators, that is, given the y's, I want to generate some estimator using some arbitrary linear combination of y. I want to use some matrix here. I don't know what matrix. So what should be the property of these matrices so that I will get something? I will get an estimator. How can I do that? So it turns out that if you put that is again data is generated, if data is generated as y is equal to phi transpose theta plus, in this case, E or V, whatever, say V, then if you take any arbitrary, what I am saying is that the least square estimator is just one linear estimator. There may be other linear estimators. In fact, there is a very important linear estimator which we will study in a future class called instrumental variables. They have very nice properties. They give you much better estimates over least square using a very computationally efficient form. So it is not that you have to always use the standard least square standard least square estimate. So what we are trying to see is that if we constructed a general class of estimators which are generated from y in some way, this t, what this t I don't know, but what should be the property of t such that if I generate it using this t, then this theta tilde, which is the error between the true and the estimated parameter, will be low if I ask this question. So if I calculate this will be my theta tilde using this equation as the data generating equation. Then it turns out that if theta tilde has to be 0, then t should have this property. Property number 1, that this should be equal to identity, and because if this is equal to identity, then this is 0 and this should be 0. What does it mean? That this matrix T should be such that it is very well correlated with the actual data phi. So it's not necessary that you have to use the data. You can use something else other than data, but you must use something which is very correlated with the data and very uncorrelated with V. If you can do that, then whatever you put in this T matrix will give you an estimator. In fact, we will see later, especially in the context of the instrumental variable, that sometimes not using the data itself has great benefits, right? So this was, so any linear unbiased estimator. What do I mean by unbiased? Unbiased means that asymptotically this theta hat will tend to theta. If that happens, then we call an estimator as unbiased. So and then you can what is an optimal unbiased estimator is that if you go further, that of all unbiased estimators, which one gives you the least covariance, that also you can ask. So fine, so we will have to close today. So before closing that, all I want to say is that, so what did we do? We first found out a basic least square solution to a problem. Then we found that under the assumption that the data has been generated using a model of the same type, we can get some good properties from the least square algorithm. That is the estimated parameter will finally converge to quote unquote the true parameter which is the system used to generate the data. That we found. And lastly, we found that it is not always necessary to go for a least square estimate. Sometimes it may be good that you will, rather than putting directly the data, you can put slightly modified data or some other matrix. Only thing is that whatever you use, you must ensure these two properties. So if you can ensure these properties, you will get what is known as a linear unbiased estimator. So we will continue with this, and we will see, especially in the next class, that there are several variants of the least square. This is the basic least square problem. You can toss and turn this problem in a little different way here and there, and you can get new estimators, which will be useful in several various contexts. So we will see that tomorrow. Thank you very much.